So my name is Gonzalo Aranda, and I'm here to showcase our new technology, that is the intelligent magneto-mechanical system to simulate physio and pathologically relevant mechanics dynamics in vitro. Okay, so stiffness and deformation has like a pretty important role in several physiological events, like cell differentiation into gastrulation type phenotype, tumor progression, like in epithelial mesenchymal transition, wound reepithelialization, and skin scar formation. If we take a look to the deformation dynamics in pathological events like ischemic stroke or traumatic brain injury, we can see there are like fundamental differences. In ischemic stroke, for example, the deformation are sustained and has like a slow pace growth. And in the case of traumatic brain injury, the deformation are dynamic, fast, and spike. Okay? So apart from the dynamics, we have to take into account that during traumatic brain injury, there are several deformation stages that produces complex strain patterns. So not only is vital to reproduce the dynamics, but also these complex strain patterns in vitro, and that's what we achieve with our system. Okay, you can see here down that we managed to reproduce in our system the local strains. Okay, so our system is composed by three main parts. Okay, being the central axis, the material. Okay, it's a cellular substrate. It's a substrate for cellular culture. Okay, that has to be like to have soft tissue stiffness in the range of 1 to 10 kilopascals, and has to be mechanical responsive to remote physical stimuli, and obviously to be cytocompatible. Our stimulation system has to be able to remotely actuate on the material to generate deformation patterns and dynamics, and obviously we have to develop manufacturing strategies through extrusion 3D bioprinting, to manufacture these bodies, okay, these cellular substrates. So in terms of the material of our choice is the soft magnetorheological elastomer, MREs, okay, that is basically composed of an elastomeric matrix with magnetic particles embedded, okay. So in the presence of magnetic fields, the material responds and deforms, okay. In our case, our elastomeric matrix is our old friend PDMS, and the magnetic particles are carbonyl iron powder that are placed in the elastomeric matrix in several concentration of particles. Okay. So in terms of the system is mainly composed by this substrate, this material substrate, and 4 sets of permanent magnets that are controlled independently, okay, and are disposed like arranged across 2 orthogonal planes. So we can modulate the intensity of the magnetic field just to moving the magnets together or just moving apart from each other. Okay, so in that way we can stimulate the cells that are seated on top of the substrate. And of course, this is aided by an advanced computational interface that just predicts the strain pattern that you are creating within that magnetic field, and provides you the position of the magnets to recreate that strain pattern. So some physical fundamentals: the deformation gradient is produced obviously by the generation of a magnetic field, and the magnetic particles just align in the same direction of the magnetic fields, creating like a chain-like structure, so the material deforms. And we develop an in silico framework just to that gives you the position of the magnets in order to recreate your desired strain pattern. So we integrate full field models with lattice-based models, micromechanical models, and continuum macroscopic models that don't only integrate the substrate and the magnets, but also the space in between. And in that way, we perform a computational validation of the displacement fields, and we can see in the video that we are able to, well, this is a render obviously, but we are able just by giving the position of the magnets to recreate the desired displacement field. Okay. So in terms of manufacturing of these MREs, there are some current strategies that are pretty amazing, but all consist on adding to the elastomeric matrix some silica nanoparticles or self-supporting that in our case may hinder the mechanical properties of the matrix, because if we modify the mechanical properties, we defeat the purpose of providing a system that recreates the stiffness of a soft tissue of a brain, for example, no? And also may lead to cytotoxicity. So it seems that we need a methodology to manufacture these MREs without the need of additives, and it is quite difficult because this elastomeric matrix transit from liquid to solid, so at first has very poor shape fidelity, but then it becomes solid, so it is impossible to extrude. And actually, this is a reaction ongoing. The mechanical properties are evolving during the printing time, so the optimal printing parameters change over the printing time. So we developed a methodology to overcome these issues, and this methodology is based on a rheological characterization that gives you the printing window of your material, an injectability characterization that gives you a pressure profile that drives the flow of your material across the whole printing process robustly and with consistency, and we provide a theoretical model that predicts the evolving printing parameters for other materials and other flow conditions, okay? And of course we validate this in an in-house 3D printer that has the ability to change the pressure parameters on the fly during the printing process. So first we start with the rheological characterization to determine the print window. So in here we studied the viscous and elastic behavior of the material in two scenarios. One low shear rate scenario, which corresponds to the material being at rest at the printing bed, and then a high shear rate scenario that corresponds to the material being extruded through the nozzle. Okay, so in each of the states we look for the crossover point, you know, the point at which viscous and elastic properties reach an equilibrium. So in that case we obtain like a start printing time and an end printing time that allow us to constantly extrude material through the nozzle. So to obtain a constant ink flow, a constant material flow, we impose a vertical displacement, okay, with a universal testing machine. That constant displacement imposes a material flow, and we are able to track the forces driving this flow. So we are able to generate a pressure profile for that material, for that given flow rate, and to introduce to the printer and just validate that it effectively recreate the constant extrusion velocity that we impose with the universal testing machine for several conditions of MREs. So the problem with this methodology is that it serves for a given material and a given flow rate. So as we aim to perform multi-material printing and also using several flow rates, we just want to fast track this process. So we provide a hybrid theoretical experimental method for robust printability of this kind of materials. First, we have to identify the print window, okay? In this case, it's two materials. So with the rheometer as the other methodology, but the difference is that just with some rheological characterization, you can characterize the constitutive behavior of the fluid and just extract the time-dependent material properties that will fit our computational model based on Cisco's model, okay? So we are able to provide a pressure profile for your given material for every flow rate that you want, okay? And of course, we validate this just comparing our methodology with a constant pressure approach, and we can see that as time advances in a constant pressure approach, the flow speed hinders, okay, is being compromised, while in the adaptable pressure approach, the flow speed maintains constant, okay? And this is validated as well in terms of shape fidelity of the sample, and as you can see in the constant pressure, the material deposition is being also compromised. In adaptive pressure, it maintains better the shape fidelity through the printing process. So now that we have a system that can stimulate, that can implement multi-material, we just want to seed some cells on top of it. Okay, we want to stimulate the cells, and we want to monitor by the use of microscope. So we just manufacture a substrate that is composed by an outer shell of MRE that is, it's magnetically responsive, and a core of transparent PDMS that allows cell visualization. So in that way, we can impose some strain patterns and just visually inspect the cells before and after stimulation and see some conformational changes. So we measure local strain by seeding astrocytes of different types of astrocytes, and we measure the strain of the branch strain, cell body strain, and this is an unpublished work, okay? I forgot to mention here in the slides. And we even are capable to generate the strain in several directions and see if there are differences between the orientation of the deformation, okay? And we can also couple the system with a nano indentation device that allows us to measure relative stiffness change of the cells at a cellular level, even in several regions of the cell, before and after stimulation, and to couple with the imaging. And right now there is a work in progress measuring calcium dynamics and cytoskeleton rearrangement, and also lactate production. So right now we are in the bridge to expand the technology to 3D systems using hydrogel-based materials. So right now we are developing a system that incorporates a fibroblast embedded hydrogel, a model of a stroma, and we just want to see if there are some changes in the extracellular matrix deposition when stimulated mechanically with different patterns. So that's it. This is, thank you for asking, no, thank you for listening, and many thanks to the Multi-Biostructure Lab and the Termec Lab from Universidad Carlos III. Thanks to all our collaborators and our founders, and of course thank you to the MPS Summit to grant me the opportunity to showcase our technology, and thank you for listening. So I'll take anything.
Thank you very much, Gonzalo. Are there questions? Then maybe I start by asking, what are you envisioning? So what type of readouts with the three-dimensional models you are generating? I mean, it's known that basically forces haven't a direct impact on cell differentiation, orientation, and things like that. So do you have like a specific question in mind?
Well, as we are also collaborating with skin tissue engineers, we are also pursuing the mechanism of hypertrophic scarring, for example, or excessive matrix deposition in terms of differentiation of fibroblasts into myofibroblasts and this kind of stuff. Yeah.
Okay, thank you very much. Any questions?
Yeah, thank you for a really nice presentation. What kind of strain rates can you achieve? So what kind of dynamics?
Well, actually, let me go back. But we are able to to well, you mean strain rates or strain magnitudes? Okay, I mean it's the frequency, periods of milliseconds actually.
Okay, so let's thank Gonzalo again for this very nice presentation.